You left me at the door last week with a threat dressed up as a promise. You said the going around, that quantity I'd finally made my peace with, was about to turn from a plain number into an arrow. An arrow that points and resists and dodges sideways away from the very hand that shoves it. You said, lean on a spinning top, and it will not fall the way anything sensible falls. It swerves off at right angles instead and keeps standing. And then you swanned off into the dark the way you do. So I've had a whole week to sit with that, and I've decided you were exaggerating. So, show me.
I was hoping you'd come in swinging, and I'm not going to argue with you. I'm going to hand you two things and let them do the arguing for me. You've got a child's top somewhere in the house, haven't you? The old-fashioned kind, wood and a metal tip, that you spin on a table.
I can picture one perfectly. You wind it or you pinch it and twist hard between finger and thumb and let it go, and it dances around on its little point.
Spin it hard and set it down leaning, not standing straight up, but tipped over at an angle like a tired little tower halfway to falling. Now, first, a top that isn't spinning, set down leaning like that, what does it do? Instantly,
It falls over. Obviously, it's tipped past its balance, nothing's holding it, gravity takes it, it topples flat onto the table. 1/10 of a second and it's lying on its side. That's not even physics, that's just Tuesday.
That's just Tuesday. Now spin the very same top, hard, and set it down at that very same drunken lean. And it does not fall.
Go on.
It leans there, tipped over, plainly off balance. Plainly by every rule you own, it should be flat on the table already. And instead of toppling, the lean itself begins to travel. The top holds its tilt, that same angle, but the direction it's leaning swings slowly around, so the whole top walks its lean around in a wide, slow circle, standing up the entire time. It'll keep at that until it tires out and slows down.
Okay, no, that's a trick top. That's a top with something in it, a hidden weight, a battery. You do not get to tip a thing past its balance and have it simply decline to fall. That breaks the one rule that everything else in the world obeys, without complaint.
Nothing in it. Wood and a metal tip, spun by a hand. And I'll raise you a stranger one. Take the front wheel off a bicycle. Just the wheel, on its axle, the axle sticking out a stub on each side. Now tie a rope to one end of the axle. Only one end.
Only one end. So it's lopsided from the first breath, held on one side, nothing on the other. That's a thing already begging to flop straight over.
You'd think so, wouldn't you? And hold the rope up so the wheel dangles from it. Wheel not spinning. What hangs and how?
It hangs like anything heavy hangs. The wheel flops down flat under the rope, the axle pointing straight at the floor, the whole thing drooping like a bucket on a string. One end's held, the rest sags. Gravity, again, doing the dull, obvious thing.
Now spin the wheel up fast and let it dangle from that same single end of the axle. And it does not droop. The axle stays dead level, jutting straight out sideways into the air, horizontal, as though it were lying on an invisible shelf, with nothing under its far end but floor. And then, gently, the whole wheel begins to travel in a slow, flat circle around the rope, like the hand of a clock, staying level the whole way round.
Sticking straight out sideways, held at one end, with the far end just out there, over nothing.
Over nothing. Held up by nothing you can point to.
That's the one that gets me, more than the top even. Because I can just about lie to myself that the top is balancing somehow, spinning on its point. But a heavy wheel jutting out flat and sideways off a rope, refusing to sag, and then strolling around in a slow circle in mid-air. There is no story anywhere in my head where that's allowed. So either you're lying to me, or the world is.
Neither of us is lying. And here's my one promise for the night, and you can hold me to it. By the time we're finished, you won't merely tolerate these two. You'll find them inevitable. you'll wonder how a spinning top could possibly do anything else but this. There is a single secret sitting under both of them, and I can tell it to you in one short sentence, though it won't mean much yet. Treat the spin as an arrow.
An arrow. That's the very thing you dangled at me last week. Fine, but an arrow's plainly the end of the story, not the front of it. What do I need under me before an arrow means a single thing?
You need the whole world of spinning rebuilt from the floor up. And the good part, the part that should cheer you, is that you already own most of the bricks. Everything we learned in the early nights about shoves and masses and momentum, Newton's whole straight-line world, has a twin that lives in the world of turning. The same laws, wearing new coats. Let me walk you through the twins, and the arrow will land in your hand ready-made.
Twins of what? Laid out how? Give me the two sides. On the straight line side, from those first nights, I had three things: a force, a mass, and a momentum. A push, the stubbornness of the thing you're pushing, and the motion it carries off. Those three.
Those three, and each has a spinning twin. Start with the push. On the straight line side, a force is a shove. You want to change how a thing moves along a line, you shove it along the line. On the spinning side, you don't want to shove a thing along, you want to twist it. Wind it up, spin it faster, spin it down. The twisting version of a shove has its own name: a torque, a twist.
A torque is a twist. All right, clean enough word. But a twist is just a force going in a circle, surely. So why does it get a whole new name? Why isn't it the same force I already had in my pocket?
Because a twist cares about something a straight shove never gave a thought to. It cares where you push, not only how hard. And you felt this in your hands, everyone has. A stubborn bolt, rusted tight. You grab it with a stubby little wrench and heave with everything you've got, and nothing moves. Then you slide a long pipe over the wrench's handle to make it longer, grab it way out at the far end, and push no harder than before, and the bolt cracks loose like it had just been waiting for you to ask nicely.
Oh, everyone's done that. The cheater bar. The longer the handle, the more it turns, even though my arm isn't pushing an ounce harder. My father kept a length of scrap pipe in the garage for exactly that job.
So the twist you deliver isn't only how hard you push. It's how hard you push, times how far out from the center you push it. Same push, twice as far out from the bolt, twice the twist. That how far out is the whole difference between a torque and a plain force. It's a force reaching out on a long arm. Push right up close at the middle and you get almost nothing. Push way out at the end of a long arm and a gentle hand shifts what a clenched fist couldn't.
Push times how far out. And that quietly explains the shape of every wrench and every door I've ever touched. You never see the handle bolted next to the hinge. It's always way out at the far outer edge.
The shape of every door, worked out from one idea. The hinge is the center. The handle sits as far from it as the door will allow, to give your hand the longest possible arm and so the biggest twist. Try shoving a door open right beside its hinge and you'll fight it all day. Push at the outer edge and a single fingertip swings it wide. That's torque, twin number one.
And the playground merry-go-round is the same, now I think of it. To spin the thing up, you don't grab the center pole and shove. You couldn't budge it. You run out to the outer rail, get a grip on the very edge, and heave from there, way out where the arm is longest. Same pair of arms, biggest twist.
Out at the rail, where the arm is longest. That's it. Nobody in the history of playgrounds has spun a roundabout from its middle. Now twin number two, the stubbornness.
On the straight line side that was the mass. The heavier a thing, the harder to get it going, the harder to pull it up once it's going. A shopping cart loaded with bricks against an empty one. That flavour of stubbornness.
The spinning world has its own stubbornness, and it carries a stuffy formal name we'll mostly leave in the drawer. But all it means is this: how hard is a thing to get spinning, and how hard to stop it once it's spinning? rotational stubbornness. And here the twin is not a plain copy of its sibling. Here's the best surprise of the three. For a straight-line shove, stubbornness was only how much stuff there is. The mass, full stop. For spinning, it is not just how much stuff. It's how far that stuff sits from the axis it's turning around.
How far the stuff sits from the middle. So two things could weigh precisely the same and still not be equally hard to spin.
That's the surprise. Take the very same amount of stuff, the same mass down to the last gram, and hold it all in tight against the axis, or fling it all out far from the axis. The one with its mass flung wide is dramatically harder to spin up, and harder to haul to a stop once it's going than the one with its mass hugged in close. Same weight on the scale, wildly different stubbornness in the spinning. Because out in the turning world, stuff far from the axis counts for far, far more than the same stuff sitting near it.
Give me that one in something I can feel in my own body. Where would I ever have touched it?
The tightrope walker's long pole. Ever wonder why they haul that great drooping pole out across the wire, held wide to both sides? It isn't for show. The pole flings a lot of mass way out, far from the walker's own middle, the line they'd pivot and tip around if they started to spill. All that far-flung mass makes them enormously stubborn against any twist, against the very beginning of a topple. The pole doesn't hold them up off the wire, it makes tipping them slow and reluctant, so a wobble that would have dumped a bare-handed walker instead unfolds slowly enough to feel it and catch it.
So the pole is stubbornness on a stick. It doesn't fight the fall head-on, it just makes the whole business of tipping so sluggish and grudging that the walker has time to fix it. And it does that by reaching wide, not by being heavy.
By reaching wide. A light pole held wide beats a heavy weight held close.
That lands. And it might be why choking up on a baseball bat helps. You grip higher up the handle, which pulls the far mass in closer to your hands, so the bat turns less stubborn and you can whip it around quicker. Same bat, you only moved where you hold it.
Same bat, mass drawn in, less stubborn to swing round. Choking up is stubbornness management, whether the batter would ever call it that or not. And now the picture I've owed you for weeks strolls back in to settle its debt. The figure skater, spinning on the ice. You met her before, but she was on loan then. Tonight she's ours properly, because now she's a body turning on itself. She spins with her arms and one leg flung out wide, and she turns slowly. Then she gathers everything in, arms wrapped tight to her chest, leg tucked home, and
she speeds up, whips herself into a blur, all on her own, with nobody pushing her. I've watched that 100 times, and it always looks like daylight cheating. And, hang on, that's the third twin, isn't it? That's the going around being kept. Let me actually call it this time instead of just nodding along. Arms in, she speeds up. I'll stake money on it before you say a word.
Take it, it's yours, and collect with a grin. Arms in, she speeds up, every single time. First clean win of the night. Now here's the machinery under it. On the straight line side, motion was carried by momentum. Mass times how fast. On the spinning side, motion is carried by the going around, the angular momentum, and it's the rotational stubbornness times how fast she spins. And that quantity, left alone with no twist reaching in, is kept, held fixed. It was the cousin locked away in its own ledger. Tonight, at last, we open the ledger.
So walk the satyr through in exactly those words. What's held and what gives way?
Her going around is held fixed. Nothing outside is twisting her. The ice is near enough frictionless that no twist reaches in to change it. So that product, stubbornness times spin rate, must stay the same number the whole way through. Now she pulls her arms in. She's dragged all that mass from far out to close in, and you just told me what that does to her stubbornness.
It drops it. Hard. Mass close to the axis is far less stubborn than mass flung wide, so hauling it in collapses her stubbornness right down.
And if the stubbornness drops, while the product of stubbornness and spin has to stay the same fixed number,
Then the spin has to leap up to make the books balance. Stubbornness falls, spin rises, and the two of them multiplied together land back on the very same number as before. She isn't breaking the rule, she's paying for the drop in stubbornness with a jump in speed. That is genuinely satisfying. It's the same conservation as the two skaters shoving apart, only curled around into a circle.
curled into a circle. And let me guard one thing here, because it's a pit people fall straight into. It is her going around that's held fixed, not her energy. Don't weld those two together. In fact, pulling her arms in against that whirl is real work. She has to drag them inward while they strain to fly out, and every bit of that effort she spends pumps her up into a faster, more furious spin. She comes out the other side carrying more spin energy than she went in with, paid for out of her own muscles. The thing kept dead constant is the going around, the energy she pours more into.
Filed and filed carefully. Going around kept, energy she pays into with her arms. Don't fuse them. All right, I've got my three twins now. A torque, a twist that cares how far out you push, a stubbornness that cares how far out the mass sits, and a going around, stubbornness times spin, that stays put unless a twist reaches in from outside. So, where's the arrow? You keep promising me an arrow.
Here it is. That going around, the angular momentum, I've let you picture it so far as an amount, a bigness, how much whirl she's carrying. But it is not only an amount, it has a direction, it points. And the moment you see which way it points, the top and the hanging wheel both fall open like a book.
A direction. But a spin doesn't point anywhere. That's the whole trouble with a spin. A thrown ball points where it's going. A spin goes round and round on the spot. Every part of it is heading a different way at once. This bit rushing left, that bit rushing right, all of them different, all of them changing. There's no one direction anywhere in the thing. So how do you paint an arrow on something that's going every way at once?
That is exactly the right objection, and the answer to it is the clever move that makes the whole subject work. You're right, you cannot point along the going round because the going round is every direction at once. So you don't. You point along the one line that isn't going round. The axis. The still line down the middle that all the rest turns around. A spinning top has one line through it that isn't whirling anywhere. Straight up the middle, tip to crown. A wheel has one, the axle. That still line, the axis, is where you lay the arrow.
Along the axle, up the spindle of the top. The one part of the whole thing that isn't itself going anywhere. That's where the arrow lives.
That's the secret, whole and entire, and it's worth saying slowly. The going around of a spinning thing is an arrow lying straight along its spin axis. For the top, the arrow runs up the middle, along the way it leans. For the wheel, it runs straight out along the axle.
So the arrow and the axle are one and the same line. Point at the axle and I'm pointing at the arrow.
The axle is the arrow, drawn in the metal. And how long is the arrow? As long as the whirl is big. A fast, heavy spin, a lot of stubbornness, a lot of speed, is a long arrow. A slow, light spin is a stubby little one. Spin the thing up faster and the arrow grows.
And which way along the axle? Both ends of an axle are the same line. How do I know whether the arrow points off to the left along it or off to the right?
Fair to pin, and I'll do it fast and not lean on it. Curl the fingers of your right hand the way the thing is spinning. Chase the whirl around with your fingertips, and your thumb sticks out along the axis, pointing the way the arrow points. That's the whole rule, and it gives every spin one definite end of the axle to point down. We won't fuss over which end tonight. What matters is that the arrow lies along the axis, and its length is the size of the whirl.
Fingers follow the spin, thumb is the arrow. I'll take it. But an arrow lying quietly along an axis is a picture, not yet a miracle. What does the arrow do that a plain old amount didn't?
This. Remember the rule the going around obeys. Left alone, with no twist reaching in from outside, it is kept. Held fixed. Now that you know it's an arrow, held fixed means far more than it did before. It doesn't only mean the amount stays the same, it means the whole arrow stays the same length and the same direction.
The same direction. So it's not only how much whirl the thing carries, it's which way that whirl is aimed, pinned in place along with it.
Pinned in place. The arrow goes on pointing the exact same way in space. Pin an arrow's direction to the heavens, and whatever it happens to be the axis of has to keep pointing that way too.
So a spinning thing, left alone, keeps its axis aimed at one fixed spot in space, because the axis is the arrow, and the arrow won't turn. That's a great many things at once, isn't it? That's why
Say them then.
That's why a thrown football spirals true. You spin it about its long axis, the axis holds its aim, so it keeps its nose pointed forward the whole flight, instead of tumbling end over end.
The whole art of a good throw in a sentence. Put enough spin on it that the arrow holds and the nose simply can't wander off. Go on, you've got more.
A rifled bullet flies straight and doesn't go cartwheeling. The spin holds its arrow. A frisbee. You flick spin into it and it sails out flat, holding its plane instead of fluttering down like a tossed dinner plate.
Keep going. There's a bigger one still waiting.
A bike. A bike stays up while it's rolling and falls the instant it stops. The wheels are spinning. Each wheel's carrying an arrow through its axle, and a rolling wheel holds its arrow, holds its plane upright, so it resists being flopped over. Stop the bike. No spin, no arrow, no help, and it keels over like anything dead. And you're about to tell me the Earth is one of these, aren't you?
The grandest one on the whole list. The Earth is a spinning thing with an arrow up its axis, the line running pole to pole, and that arrow holds its aim out in space, which is why the Earth keeps its tilt steady, year after year, all the way around its orbit, the axis leaning by the same amount, aimed at the same far part of the sky, whether it's on the near side of its journey or the far. It's clutching a fixed arrow, same as the football, only slow and enormous. That steady tilt is nothing but the going around holding its direction. On the bike, one caveat. The spinning wheels lend a hand to keep it upright. They aren't the whole of the story, but the stubborn arrow is really in there, pulling its weight.
Let me say back what I think I'm now seeing, because something's quietly rearranged itself. This whole while I've been calling these things stable, the football, the bike, the top, as if the object itself were bracing, gritting its teeth, refusing to be knocked down. But that's not it at all, is it? The object isn't resisting a thing, it's the arrow. The arrow won't turn, and the axis is welded to the arrow, so the axis can't turn either. The stubbornness isn't in the wood, or the leather, or the metal. It's in a direction that simply will not be moved.
That's the whole of it, and you've put it cleaner than I would have. Stability isn't the thing digging in its heels. It's an arrow that won't change direction, dragging the axis along behind it wherever it insists on pointing. Hold that tight, because now we can walk straight up to the two impossibilities from the top of the night, and you'll watch them stop being impossible.
The leaning top, yes, come back to it because it's still lodged in my chest like a splinter. If the arrow just holds its direction, fine, I'll grant that keeps a bike up or a bullet flying nose first. But the leaning top is not left alone, is it? Gravity's on it. Gravity's hauling down on a top that's tipped clean past its balance, and I know precisely what gravity does to anything tipped past its balance. It pulls it over. So, off you go. Set the spinning top down leaning, gravity grabs it, it falls over. same as the still one, maybe a touch slower on account of the spin. That's my answer, and I'm fairly well sure of it.
Good. Plant your flag on that hill, because this is the one you're going to get wrong, and I want you to feel it go out from under you. So, the top leans. Gravity pulls down on it, out at its heavy middle, away from the little pivot it's spinning on, and an off-center pull like that is a twist, a torque. Gravity is trying to twist the top over, precisely as you say, to swing it down onto the table. On a still top, that twist wins instantly, and over it goes. And you're sure the spinning one does the same?
I'm sure. It's leaning, it's heavy, gravity's twisting it down. It falls.
It doesn't fall. Not a hair. And the reason is the one rule you now hold about arrows turned loose on a twist. A twist changes the going around arrow. That's what a twist is for. It's the spinning world's version of a push, changing motion. But look hard at what it's pushing on. The going around is a great long arrow, lying nearly flat, pointing out along the leaning top's axis. And gravity's twist does not push that arrow down. A twist pushes the arrow sideways.
Sideways. Wait, say that again, slowly, because something just went badly wrong inside my head.
Slowly then. Gravity's twist, working on that big, nearly flat arrow, does not tip the arrow down toward the table. It nudges the arrow sideways. It swings the tip of the arrow around horizontally, level. And because the top's axis is welded to that arrow, when the arrow swings sideways, the whole top swings sideways with it. It does not tip over, it turns. The lean stays the same size, and it just travels. The top pivots the direction of its lean around in a slow circle, which is the exact walking around its lean you refused to believe an hour ago.
No, hold on. You're telling me gravity is hauling the thing down, straight down, honestly trying to tip it flat, and the top answers by going sideways. You push it toward the floor, and it moves along the floor instead. That is not a thing that is allowed to happen. Push it forward and it goes sideways. Who signed off on that?
Nobody signed off on it. The world simply works this way, and it took clever people a long, sore while to make their peace with it.
I want it on the record that I am actively not at peace with it. Go ahead.
Nobody is, the first time they meet it. Here is the rule, said plainly, and if you carry one thing out the door tonight, carry this. Push a spinning arrow, and it does not move the way you pushed it. It moves at right angles to the way you pushed. Shove the arrow down, and it swings off to the side. Every time. The top doesn't fall because gravity's twist isn't a topple. It's a sideways swing, delivered at right angles, and it turns the axis in a circle instead of tipping it into the table. That circling of the axis has a name. Precession.
Precession. The top precesses instead of falling. And that slow circle the leaning top walks, that's the arrow being swung sideways, round and round, by a gravity that's pulling straight down the entire time and never once manages to tip it.
Never once manages. Gravity is hauling down the whole time. The top absolutely feels it. It isn't shielded. It isn't weightless. It's being twisted hard every instant. But the answer to that twist isn't a fall. It's a turn.
So the top isn't beating gravity, and it isn't dodging it either. It's paying gravity off in a different coin, handing over a turn where you expected a fall.
A turn where you expected a fall. That's the coin precisely. And I'll flag the trap right here, because this is the spot where people slide off. Gravity's twist is not secretly speeding up the top spin, and it is not being politely ignored either. It's spending itself, all of it, on swinging the arrow sideways, changing where the arrow points, not how long it is, and not tipping it down. Direction, not size. That's precession.
Then take me back to the wheel on the rope, because I want to try to call this one myself now, and see if your sideways rule saves it. The spinning wheel dangles from one end of its axle. Gravity's pulling down on the wheel, out at the far end of the axle, away from the rope. So that's a twist, trying to fold the far end down, trying to droop it flat the way the dead wheel drooped. But by your rule, that downward twist doesn't get to fold it down. It gets answered at right angles, sideways. So the far end of the axle doesn't drop, it swings around sideways instead, and the whole wheel wheels around the rope, level, chasing a fall that keeps coming out sideways. Is that right?
That's right. First word to last. The hanging wheel doesn't droop because the droop keeps being turned into a sideways swing. So it sails around the rope, dead level, forever chasing a fall that never once arrives. Which is exactly the thing you flat refused to believe when I first set it in front of you. Same rule as the top. Gravity twists, the arrow answers sideways, and what should have been a plummet becomes a slow, patient circle.
That is a wholly different feeling than an hour ago. An hour ago, the hanging wheel was a magic trick, and I was sure it hid a wire. Now it looks like the only thing the poor wheel could possibly do. You did warn me that would happen. I somewhat resent that you were right.
Then let me push my luck and try to make you feel why it's sideways. Not just take it on my word, but half see the gears turning. This next bit is a picture, not the proof. An intuition, a hand on the shoulder, not the full airtight machinery. The complete story is heavier than anything we need tonight. But the picture gives you the true behavior, and it's worth carrying.
I'll take the hand on the shoulder. Go on.
Freeze the leaning top for one instant. There's the big arrow lying along its axis, long and nearly flat. That's the going around it already carries, and it's huge because the thing is spinning fast. Now, what is gravity actually trying to do to it? Topple it. Tip it flat onto the table. But look hard at what a topple even is. It's a turn. For the top to keel over, it has to rotate, about a flat, level line running along the table through its foot. And we own the rule for that now. A spin about a line is an arrow lying along the line. So the scrap of spin gravity is trying to feed in is an arrow along that flat line. Laid horizontal, off at right angles to the tall arrow already standing up the axis. On a still top, that little sideways arrow simply is the fall. Nothing opposes it, so the top tips and goes. But on a fast top, all gravity can do is tack that small sideways piece onto the tip of the enormous arrow already there. And here's the crux of the whole thing. The little bit it adds doesn't point along the big arrow. It points off to the side of it. A small sideways piece welded to the tip of the big one.
A little sideways stub stuck onto the end of a big, long arrow. All right, I'm picturing it. The long arrow and a short piece being welded on at its tip, poking off to the side.
Now, what does adding a small sideways piece to the end of a big arrow actually do to the big arrow? It doesn't make it longer. The piece is off to the side, not out along it. And it barely tips it. The piece is tiny next to the great length of the arrow. All it can do is swing the arrow's tip over by a hair. It pivots the whole long arrow through a tiny angle, sideways. The arrow doesn't grow and it doesn't drop. It just swivels a little. The fall becomes a turn.
Because the new bit points sideways, so all it can do is steer the arrow. It can't stretch it and it can't drop it. It only nudges its aim over.
And gravity doesn't do it once. It does it continuously, every instant, on and on. Each instant, another little sideways piece, another hair of swivel, another and another. And an arrow that keeps getting swiveled sideways by the same small amount, over and over, doesn't wander off somewhere new. It comes back around on itself. Its tip traces a circle.
A circle, because each nudge turns it the same little bit further around the same way, so there's nowhere for the tip to go but back to where it began. And round again.
Round and round, forever chasing itself. The arrow sweeps out a cone, and the axis riding along it sweeps the very same cone. That cone, drawn in the air by the top's axis, is the precession. It's the slow walk of the lean.
The arrow chasing its own tail around a cone. And because every single nudge is small and sideways, it never piles up into a fall. It just keeps curving the aim around the circle and back. That I can actually see.
And it hands you a bonus your own intuition can now predict. Suppose the top is spinning faster. A longer arrow. Same gravity, same little sideways piece added each instant. But now that piece is being tacked onto a much longer arrow. A small sideways stub swivels a long arrow through a smaller angle than it swivels a short one. Same nudge, bigger thing to turn. So a faster spinning top processes slower. It walks its lean around more lazily, and it stands up stiffer and more stubbornly upright the faster it goes.
So the faster it spins, the more sluggish and dignified the circling, and the more rock-solid upright it holds. And a top that's winding down, losing its whirl, a shorter and shorter arrow, must process faster and faster as it tires.
Which is the very thing you watch at the end of a top's life. It spins down, and its stately, slow circle winds up into a frantic wobble. Quicker, wider, lower, until at last there's not enough arrow left to answer the twist sideways anymore. And then, only then, gravity finally collects its topple, and the top clatters over on its side.
So the wild death wobble at the very end isn't the top breaking down or giving up. It's the same procession as before, only racing now, because the arrows run too short to keep it dignified.
The same procession, sped up because the arrow's grown short. The top earns its fall right at the end, when there's too little of it left to save. But while it's spinning fast, that arrow is long, and the twist can do nothing to it but walk it round in a slow, patient circle.
I want to sit in that a moment, but there's another one, isn't there? Another spinning thing that misbehaves.
There's one more, and it's my favourite of the lot, because you can test this one yourself in about the time it takes to say so, and you will not believe it even while it's happening in your own two hands. Everything so far has been a thing spinning about one axis, but any solid object, a book, your phone, a tennis racket, has 3 different axes it could spin around. 3 natural ways to flip it.
3. Okay, take a book. I can flip it forward, cover over cover, tumbling end over end. I can spin it flat, like a turntable, like a plate on a table, and I can roll it the 3rd way, over along its own spine. Forward flip, flap spin, spine roll. 3 axes, 3 flips. That's the 3.
Those 3. Now, before I give it away, most people's gut picks the flat spin, the plate one, as the shaky one because it looks the least steady.
I'm not even going to guess. You've got that card-sharp grin going, which means anything that looks obvious is a trap. Just tell me, and then I'll go prove you wrong.
Here's the fact then, told flat, and then I dare you to go check it. 2 of those 3 flips are steady, and 1 is not. Spin the book cleanly about the first easy axis, and it turns over neat and true, holding its flip. Spin it about the second easy axis, same story, clean, obedient, holds its line. But spin it about the 3rd one, the awkward one, the in-between axis, and it will not hold. It refuses. Partway through, all on its own, with nobody laying a finger on it, it flips itself right over, end for end, and then does it again and again. It tumbles. It cannot spin cleanly about that middle axis to save its life.
That can't be a real distinction, though. It's the same book. If I throw it hard enough, cleanly enough, about that middle axis, surely it just...
No amount of clean is going to save you. And I'm not going to sit here and argue it. I'm going to send you straight to the referee, and the referee is your own hand. Go find a book, a nice fat one, and snap a rubber band around it so it can't flop open. Or grab your phone, locked, so it doesn't go dialing someone from mid-air.
Hold on, I'm actually getting up for this one. Right, fat paperback, rubber band on, armed and dangerous. Walk me through the 3 throws.
First, the spine roll. Spin it about its spine, the long way, like rolling a log. Clean, it holds true. Then the flat spin. Flat, spinning like a plate on a table. Clean, it holds that too. But now the forward flip. Cover over cover, end over end, the front to back somersault. And watch it. It'll start clean, then partway through, all on its own, it snaps a half twist and slaps back down facing the other way. Every single time. You'll throw it 10 times over, trying to prove me a liar, and it'll flip on you 10 times out of 10.
I am not going to make it to the end of this episode without doing that, am I? Everyone listening is right now digging down the side of the couch for their phone. All right, say I do it, and it flips every time the way you're so pleased about. Why? What is so special about the middle one?
The full why of that middle axis is genuinely hard. Real work, well past any hand on the shoulder, and no quick little story would be the true reason. So I'll give you the fact and keep the proof in my pocket. Of a thing's 3 axes, the 2 extreme ones, the very easiest to spin and the very hardest to spin, are both steady, and a spin about either one holds true. But the one in the middle, the in-between one, is unsteady, and the tiniest wobble in it grows and grows until the whole thing tumbles end over end. 2 safe axes and 1 treacherous one sitting between them.
So it isn't my clumsy throwing at all. Even a flawless throw would tumble because the middle axis is booby-trapped by the geometry itself before my hand ever enters into it. That is a genuinely unsettling little fact to be carrying around inside every object I own. Every book on my shelf has one secret axis it simply cannot spin around.
Every one of them. And it isn't a flaw you could sand off or engineer away. It's woven right into what it means to be a solid thing with 3 unequal axes. A phone, a paperback, a spun wingnut, a wrench tumbling across a room. State it, trust it, test it in your kitchen tonight, and let the deep why be a knot for the people who love the heavy machinery. What matters for us is that it's one more thing the going around does that plain common sense flatly refuses to see coming.
All right, I walked in here certain you were exaggerating, and I'm now a little frightened to spin anything in my own house. So tell me where this actually lives. This can't just be tops and party tricks. You keep hinting it's load-bearing. Where does a spinning arrow do real work out in the world?
In more places than you'd ever guess. And start with a compass. A compass with no magnet anywhere in it. Think how you'd find north with nothing magnetic at all. You take a wheel and spin it up fast, so now it carries an arrow, and that arrow wants to hold its aim in space. Mount it cleverly on a turning planet, and the spinning Earth gently coaxes that stubborn arrow into lining up with the Earth's own axis. So the thing swings itself around to point at true north and holds there with not a scrap of magnet in it. A compass made of nothing but a fast, stubborn spin. Ships and aircraft lean on exactly that.
A compass with no magnetism in it at all, finding north purely by being too stubborn to let its own axis be turned aside. Now I'm wondering how many things in my own house are quietly running on this, and I never once knew.
The thing in your pocket. Your phone knows which way you've tipped it. Knows up from down. Knows the moment you've turned it on its side to watch something. Part of how it knows is tiny sensors buried in the silicon that feel the going around itself as you twist the phone about. The same quantity as the wheels, only sensed in something smaller than a grain of rice.
So the reason my phone knows it's been turned is the same going around, read off by something microscopic, tops all the way down.
Tops all the way down. And out past the air entirely. A spacecraft drifting in the empty dark, with nothing whatsoever to push against. No ground, no wall, no water, no air. How does it turn itself to aim a camera at some distant world and then hold that aim rock still with nothing to push on? It carries spinning wheels inside its own belly. Spin a wheel up one way and the craft itself turns gently the other way. Trading the going around back and forth with its own wheels, the skater's trick worked on purpose.
So it's the skater out in the void. It can't shove off anything, so it shoves off itself. Spin a wheel one way, swing the whole body the other, and the books stay balanced at nothing.
It shoves off itself. That's the whole of it. And to hold an aim dead steady against every little nudge, it braces on those same stubborn spinning arrows. It steers, and it steadies itself on nothing at all but spin.
And a coin, surely. Spin a coin on a tabletop, and it stands up proud on its edge, going round and round, when the same coin set down flat wouldn't balance on its edge for a heartbeat. That's the arrow again, isn't it? Holding it upright.
Standing tall on its edge for no reason but that it's spinning. And the instant it slows and the arrow runs out, over it goes and rattles flat. And now the grandest member of the entire family, the one I've been holding back. The Earth.
You said it keeps its tilt because it's clutching a fixed arrow. But you said it with a look, like there was a but loading up behind your teeth.
Here's the but, and it may be the loveliest thing in the whole night. The Earth's arrow is not perfectly, forever fixed, because the Earth is itself a leaning, spinning top, and there are gentle twists working on it, faraway tugs pulling on its bulging middle. And so the Earth does the one thing you now know a leaning, spinning thing simply must do when a twist works on it. Its axis precesses, never falling, never ever falling, but its axis sweeps very, very slowly around a great cone in the sky, exactly like the walking lean of the little wooden top, only ponderous past all imagining. The star we call the pole star that we steer by was not the pole star in the deep past, and won't be the pole star in the far future, because the whole Earth's axis is slowly, grandly walking its own lean around the heavens.
The entire planet, doing the leaning top walk. Over how long? No, you won't hand me a number. Over ages.
Over ages. So slow that a whole human life is a single quiet tick of it. The axis creeping around its cone across many, many thousands of years. Whole civilizations rise and fall and steer by a north that has quietly shifted under them, and not one of them ever feels the turn, because it takes longer than all of recorded memory just to nudge the pole a finger's width across the sky. The most enormous and most patient top there is, processing away in the dark in the exact same way the little wooden one does on your kitchen table. Refusing to fall, swinging its lean around instead. Same arrow, same rule, same sideways answer to the twist. Only the size of a whole world.
Wind it up for me then, the way you always do at the end, because I marched in here fully loaded to call you a liar, and I would like to walk back out holding the whole thing in one piece. Give it to me in one breath.
In one breath. Spin is an arrow. It lies along the axis of whatever's turning, long when the spin is fast and heavy. Leave it alone, with no twist on it, and it holds its aim out in space, and that's stability. The football, the bullet, the rolling bike, the tilted earth, each one clutching a direction that will not be moved. Put a twist on it, and it doesn't do the thing you'd swear on your life it must. It doesn't fall the way you pushed. It swings sideways, off at right angles, and the axis walks around in a slow circle. That's precession, the leaning top that circles instead of toppling, the wheel that hangs out level and wheels around its rope. And one last quirk in the tail. Spin a thing about its awkward middle axis, and it can't hold. It tumbles end over end, in your own hand, every time.
And the two impossible things from the top of the night
were never impossible for a single second. The leaning top that won't fall, the wheel hanging out sideways in the air over nothing at all. You now know they had no choice in the matter. A fast arrow, a sideways answer to gravity's twist, a slow circle in place of a fall. Not a trick top, not a hidden wire, just an arrow, doing the one thing arrows do when you push them wrong, going sideways. The magic was inevitable the whole way along.
It really was. And I'm a little sorry it isn't magic anymore, but only a little. So, where do you leave me this time? You've got the look on. There's a door somewhere, and you're about to fling it open and stride through it and leave me squinting after you into the dark again.
One more door. Every single night of this whole series, the very first law, the swinging pendulum, the orbits, tonight's tops, we've watched the world from one honest place to stand. A steady spot. Solid ground that isn't itself spinning or lurching. A fair vantage where a thing left alone simply coasts and the laws come out clean and plain. We've leaned our whole weight on that steady ground the entire time and never once turned around to question it.
The steady place to watch from. The one you set down for me on the very first night. Yes.
But tonight was all about spinning things. So let me leave you with the question that pulls the floor out. What if you are the one who's spinning? What if the steady ground isn't steady because you're standing on a merry-go-round or riding on a turning planet, watching the whole world go by from a platform that's itself wheeling around? What happens to the clean, plain laws then?
I'd guess they'd start looking wrong. If I'm the one turning and I don't feel it, then things would seem to move for no reason. Something would shove me, and there'd be no hand anywhere to have done it.
Forces would seem to bloom straight out of thin air. A push that flings you outward on the merry-go-round with nothing behind it. A wind that curves as it crosses a turning world, bending for no reason you could ever point at.
The merry-go-round one I have actually felt. That hard shove outward when the thing whips around, like a hand planted in the small of your back throwing you off the edge. And you look, and there's no hand.
There's no hand. Ghost forces. The costume forces I've been promising you and dodging since the orbit night. The disguise that inner wall on the orbit was wearing all along. Real enough to knock you flat on your back, and yet there's nothing there. They come from you being the one who spins.
The forces that aren't there.
The forces that aren't there. And that's for next time. Now, give me the image to carry out. You always make me hand you one, so tonight you turn it around and hand one back to me. What are you keeping?
The top. The little wooden top, leaning like it's had one too many, tipped clean past all good sense, and simply, flatly declining to fall. Gravity's hauling down on it the whole time, honestly trying its hardest to tip it flat, and the top just walks its lean around in a slow, patient circle, standing the entire while, because there's an arrow up its middle, and you cannot push an arrow over. You can only ever steer it sideways. That's the one I'm keeping, and the next time I spin a top on a table, or hang up a bicycle wheel, or watch a football spiral in dead straight to a pair of waiting hands, or look up and think about this whole great tilted planet very slowly walking its own lean around the sky across the ages, I'm not going to ask why it doesn't fall anymore. I'm going to ask the better question, the one you handed me tonight, not why won't the thing topple, but which way did the arrow go?